Hello and welcome back to Calculus 1 Saturday edition for our last lecture of chapter 3, which is 3.11 on related rates. So we are going to have finally one applied section which you can use to make money. Let's say you want to be an engineer, right? Today we are going to discover what it means to be an engineer, the real engineer, the design engineer, the one who's actually designing parts and concepts, right, for something. Well, you're not designing concepts, you understand concepts of how something works, and then you build it. So we're going to see how's the calculus used for that, and we're going to find a lot of other interesting uses as well. So let's start with understanding the title first. So when you say related rates, you first understand the word rate, which in the past we know it is the derivative, and then the word related means, right, there's a plural on rates. So related means you will have a couple of different derivatives working together in the same equation, so we can calculate concepts. So if I have so first, like I'll say the word rate is going to be equal to derivative. So this should have been in blood. There we go. There we go. All right. So the word rate means the derivative. That's what it is. That's what it means. And we are going to now take a look at the very basic idea over here of a little square which has a side length a all around. It's a square. And what happens is when you heat, let's say you make this out of some thin sheet of metal. So you have a little piece of, imagine cutting a piece of paper, cutting a little square out of a piece of paper, and then actually having it to be a metal, not a paper. So something thin. If you put that over a flame, it will do what all objects do when they're heated. And what's that?
Melt.
Well, we're not gonna heat it to the melting point. We're putting it above a little bit of a flame. What happens when you...
It becomes flimsier.
Okay, it's still not what I'm looking for. All that is correct. What happens to all objects when they get heated?
Kinetic energy increases.
That's perfect. Kinetic energy will increase, but the object due to that expands, becomes bigger. That's something that you have to know. And we are going to actually see that concept.
Well, ice, when it gets heated, doesn't the volume decrease?
No, the volume, it turns into a liquid. It melts very quickly. Ice is a really strange thing, because ice is solid on a low temperature, and then it quickly turns into water and then evaporates with the further heat. But
like the volume of ice is greater than the volume of liquid water.
What do you mean it's greater?
Because of the hydrogen bonds in the water molecules. As it freezes, it expands.
Yes, that's correct. All right,
so
well.
The volume would be bigger. Anyway, that's chemistry. Never mind, doesn't matter.
Well, no, it does matter, because I am definitely going to look into dynamics of ice. I was going into, the metal and all of the, solid objects that when they're heated, they but then ice is solid, and I am going to look into it. But if I'm going to now without looking it up, obviously, and learning about it more, I'm going to just, you know, go and say the metal. So when you heat the metal object, it expands. And we'll see later on where those things are actually used. Now, for our little piece over here, it will expand a little bit on the two sides, which makes, I'll use this little dashed lines like this. So note that the side A grew by a little, but also the perimeter and area of the whole thing grew. So if I want to study area, which is A squared, which is side times side, we can also call it X if you want to. Let's call it X actually, because in this case you will not be confusing lowercase and uppercase. A. So area is going to be X squared. And what happens with this is now I can study the change in time. So apply d dt to study the change in time. When you heat an object, it takes time for it to expand. It doesn't instantly expand. And everything that we do in this particular section, 3.11, will be done and changed and observed through time. So all of our derivatives are in respect to time, yet our variables will be lengths and you'll see what else, right, as we go along. So now I have to use the implicit differentiation to take the derivative so that I can study the change in time for this little piece of square metal. So what I'm going to do here is I'm going to take the same formula, so write this in the new line, and we are going to take the derivative in respect to time. And now we have a lot of implicit differentiation on our hands because your variable doesn't match the derivative that we are, right, at our independent variable. So we are taking the derivative of area in respect to time and the derivative of length, which is x, in respect to time. So what do I get? Well, derivative of a is 1, and then I have to follow with the chain rule dA dt because they don't have the same variable. Equals 2x, and then I have dx dt in this side because, again, I took the derivative of variable x in respect to t. It's not the same variable. I have to follow with the chain. Now, I don't need this 1 in front over here, so I'm just going to get rid of it. And look at it. This formula here is called related rates model. What do I have in this formula? I have here rate of change of area in time, and over here I have rate of change of the length of the side in time. And with this formula, as engineer, I can learn a lot just because I took the derivative of this without knowing a concept, without having a concept of expansion and area or anything like that. I see that if the side length increases because they're both positive, the area of the object will increase. So they both increase or decrease together. So the more the one of these two grows, the more will other one grow, and the same for shrinking. They're called related rates because they are related by this, the rest of the formula that we have. And obviously these will change with every problem because you're going to have a triangle, a cone, a pyramid, a cube, and then we'll see what else, a circle, right? And then we'll see also what other things we can do with this. It is absolutely amazing how many applications, for how many applications we can use this thing. So now I can say that my problem over here, we can say that the change in length is 1 inch per hour when x is, let's say, 10 inches long. I'm just making up numbers. Who cares? And this will immediately ask a question: how fast is the area changing in time? Now, the next problem will put this into perspective of why would you want to know something like this, for instance. So when you take a look at this, you say, oh, I have the units over here tell me that I have some length over time. Look, length over time. So you immediately know what this is without being explicitly told dx dt is. You know because the units tell you that's what it is. So now from here I know that dx dt is equal to 1 inch per hour. We can maybe do 0.1 to make it nicer. And it's not, nothing's going to expand an inch in an hour. So 0.1 inch in an hour. Make it a little bit nicer. And when the length is 10 inches, well, that's clear. So now I can calculate the change in area. 2 times 10 times 0.1 is 2 inches squared per hour. So now I know that I'm going to gain 2 extra square inches in 1 hour, right, as this is expanding. Now, where would something like this, right, when things expand, when they're heated, where would this be important? And too bad that no one is a car enthusiast, but what we drive right now, like most of the people, what we drive are these very inefficient, horrible cars that we have, which explode dead plants and animals in the engine block to propel us to go forward, right? Because that's what oil is. It's just dead plants and animals from millions of years ago and so on. So what you have over there is a cylinder, right, which moves up and down due to explosion in the engine block. And then there are some piston rings that are fitted on that piston. So if you look from a side, again, this is a cylinder. This is a cylinder that goes in here, and that cylinder is connected to the shaft, which turns through the transmission turns the wheels. What happens here on the bottom is you put in a fuel, you put in oxygen, and you have a spark plug on the bottom. When you mix oxygen and the fuel and the spark plug fires up, it explodes that mixture, and the forces push the piston up, and the piston turns the the shaft and it goes, and you know, the power is transmitted. Well, you have explosions which create heat, so everything expands. These rings that sit around, they have to be tight enough so the air of explosion is not escaping on the sides. See that? Right? So it has to be tight enough, but it can't be too tight because it will be rubbing against the engine block and it will move up and down. So these precisions have to be done correctly, and then you have to compute the expansions around it. It's a 3D expansion, obviously. So that you have to know material science to see what kind of metal you can use, because if the engine is 2000 degrees and you use something that melts at 1500, then you just have a soup in there, right? Hot soup, but it's not going to work. So you have to be very careful with so many aspects when you are a real engineer designing, you know, things. These are the things that you have to be very careful about. So whether it's the volume that it's expanding or the area that it's expanding, right? We want to compute those things and understand how they work and why they work that way. And then when we have information, right, then we can do the better design. Now, we might run into a problem, right, with that later. Depends on what they have in the homework. We'll take a look. But I just wanted to bring this initial story on, right, related rates and related rates kicking in. So you are always going to have a formula that is your basic algebra or whatever formula you learned any time in life, which is a perimeter, which is the area, which is the volume, distance formulas, and a whole bunch of other stuff we'll see. But you know, the trig and Pythagorean theorem, again, distances with the Pythagorean theorem. So a lot of cool stuff. And then you are going to take the derivative of that formula using implicit differentiation to come up with the equation which is the related rates model. And that's the one where you are plugging your numbers in. So that's the one that tells you how one rate impacts the other rate. You can also have 3 different rates. We'll see that, and more than 3. So a lot of cool things that you can compute with this. Now, let's take a look at another area problem. Now, I'm lifting this problem from the book because it is really cool problem, because it's not per se engineering. It is, but it's the oil that you know, spilled in the ocean. And if you have an oil rig somewhere drilling and something goes wrong, the oil starts spreading around that oil rig on top of the surface of the ocean or the sea or whatever, in these concentric circles. So you can see that the radius of this ecological disaster is growing in time. The longer you wait, the more oil has to be cleaned up later on. So and again, this is only happening on the surface. It does not, you know, the oil floats on top and sits on top of the water. So at least it's easy to scoop. I mean, there are special ships and stuff outfitted for that job, but you know, you don't have to dive all the way down to get all of these things. So now, when you are calling the agencies, they're doing the cleanup and so on. What is the rate of expansion of this oil? What is the amount of surface area that we have to clean up, right? Because of this issue. So again, your thought process has to be, oh, the oil sits on top of the water, therefore I'm just talking about the surface area of a circle. I know what the area of the circle is, r squared pi, or pi r squared if you want to put the constant first. And I know that all of this is getting worse by the minute, right? Or by the hour. So the longer I wait, right? So I have to take derivative in respect to time, because that will give me a related rate of how far the radius, right, grows to how much the area connected to that radius is growing. So I can go and say, okay, let me take the derivative in respect to time, because the problem is getting worse in time. And here I am again taking the derivative of area, that's going to be dA dt. Copy the constant pi. The derivative of r squared is 2r, and I have dr dt, because again I was now talking math only, right? I'm taking the derivative of r in respect to t. It is not the same variable, therefore there is a chain rule following. Now you have your related rates model. dA dt is 2 pi r dr dt. There we go. And this one is going to be your related rates model. So now you have a formula that will tell you how quickly is the area of pollution, right? The area, affected area, is growing when the radius reaches certain length in r and its own rate of expansion. If you take a look at the picture and you see these concentric circles that I drew, right? All of this motion, right? All of this stuff is expanding out like this. It just goes everywhere. And the radius is also growing. So you have the radius, you have the growth of radius, and because the radius is growing, the circle area, entire area, is growing in all directions around this rig. So now we can lift the numbers, right? They say an oil rig springs a leak in calm seas, and the oil spreads in a circular patch around the rig if the radius of the oil patch increases at the rate. Radius of the oil patch increases at a rate of 30 minutes per hour. How fast is the area growing or increasing or whatever when radius is 100 meters? Again, you have all of the numbers given with units. Also, the word rate is attached to 30, and the unit is a single meter, which means a single length. So this dr dt has to be 30 meters per hour. 30 meters per hour. And we know that the radius is 100 meters because that is clearly stated in the text. And then look, how fast is the area growing? Guys, fast. Change in area in time. You see the peanut right there? Change in area in time. When I say how fast are you going? That's change of position in time, which is velocity, which is speed, right? So as soon as you see the wording how fast, that means, okay, I'm measuring a change in respect to time. That's how fast. That's what it means. in the language. That's what it means, right? You're measuring the change in time. How fast? How fast can you speak? How fast can you drive? How fast can you swim? How fast can you eat? It's all always in time, because the fast is measured in time. So now we are also asking here, how fast is the area changing? Well, we just need to stick the numbers in the formula which we discovered, right? And so you will see your main problem is always to figure out the formula, do the derivative correctly, and then plug correct numbers where they belong. So it's not always as straightforward as these problems are, but you know, we'll get there. So what do I have? I have 2 pi r dr dt. Your formula was 2 pi r dr dt. There we go. All together is 600 pi meters squared per hour. What does this mean? This means that pi is about 3.14. Call it a 3. So you can call this 600 as 1800 meters squared will be added in that hour when radius started at 100, when radius reached 100 meters. That rate was lower because look, if you want to do the same problem, right? If you keep your dr dt constant at 30 meters per hour, because this is controlled by the size of the hole through which the oil is pouring out from the rig. The bigger hole will increase this number. Smaller hole will decrease it. Well, we have a hole that supplies 30 meters per hour of ruined water, right? Polluted water. But at some point, the radius was only 5 meters, right? We can see that the change in area is much smaller. This is why you want to act as soon as possible, because affected area, dA dt, the change in affected area, right, would be 2 pi times 5 times 30, right? And that is, what is that? 10,300 pi meters squared per hour. So you see, it's a half of the value.
Professor,
Yes.
is that 6,000?
Oh yes. Thank you. 6,000.
Oh, and I guess the engineering perspective, we would approximate that value, correct?
Oh yeah. You would say you would never give a 2 decimal point for covering the area of 6,000 pi, which is 18,000, right? You just use the word about. That's, you know, the word about is good enough, especially when it's a crisis situation. Yes, this is 6,000, and this is only 300 in this case below. Wow, I did not catch that. I'm having a terrible day. Anyway, so this is what? So this is roughly 1,000 meters squared per hour added of pollution. And this is 18,000 roughly. It's more than 18,000, roughly 20,000, let's say. I'm going to see what is the what do we get when you multiply 6,000 by pi. I'll use the pi from the, so it's 18,850. So about 18,850. Now that, you know, 18,850 is way too busy of a number. So you can either say about 19K, or you can even say 20K, you know, to emphasize urgency, all right, to start the cleanup as soon as possible. But you see the idea difference between 1K and 20K of surface area added in 1 hour. The sooner the cleanup crew is there, the less area they will have to clean, the less money you have to pay for the cleanup, obviously, right? If you want to keep the business and drilling and all of that stuff in the future, right? And then you go hashtag whatever drilling companies had these things, and pretty much all of them do. So that's the idea of related rates. You always start with the equation, with the formula, and then you take that derivative in respect to time to see how fast the concept is changing, and then you go on and you compute those things. So let's see another really cool problem. Also one of the favorites. So we're going to put an airport right here. We're going to have one plane have this approach. We're going to have another airplane have this approach to the airport. We'll put this one obviously on x-axis and this one on the y-axis. And they're both traveling towards the airport. One thing is for sure, we do not want these planes to meet at a single point. What does that mean if they meet at a single point?
You crash.
It's a collision, right? So what we want to know is we want to know the distance d in between these two planes. Because when these two planes move closer to the airport, what's happening with the distance between the two planes?
It's getting smaller.
It's getting smaller, exactly. So I would like to come up with mathematical equation which will connect these concepts and see what we can do for this situation. Now, let me know, like, what does this geometry look like to you?
Right triangle.
Right triangle, great. And are there any cool formulas that would relate lengths of the sides of the right triangle?
Tons of them.
Well, give me one.
Sine,
Pythagorean theorem.
cosine.
I'll take the Pythagorean theorem. Now, why am I not taking trig? Because trig contains angle. Anytime you say sine theta equals to blah, 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 there is this angle theta, which means that you are dealing with one of the angles. And we don't have that labeled on the picture as something that is necessary. So what I'm going to say here is, for the triangle, you have Pythagorean theorem, you have trig, that's angles, you have area, you have perimeter. So these are your formulas that are available to you for a triangle. Perimeter to go around, right? Area, the size of the triangle. Trigonometry will be lengths plus angles. Maybe I should say theta plus length, and Pythagoras is only length. So when you are looking at the triangle, you look at this triangle and you say, oh, okay, so for this Pythagorean, for this one, I'm not talking about the area, because these planes fly in a straight line. You know, this plane is not going to cover like this, right? Taking on every, right? That will be area. It flies straight in. So this problem only contains lengths. That's it. And that's why Pythagorean theorem is the only choice that we can make. Now, someone will say, well, perimeter is only one that, yeah, but what is the perimeter? Right? And is that what the planes are doing? Right? Going around in a triangle like that? The answer is no, right? They just go to the airport and they land. They line up, obviously, first, and they land. So now, what am I going to do here for this particular problem? Well, I am going to write the Pythagorean theorem. In my case here is x squared plus y squared equals d squared. That's the Pythagorean theorem. Because I have this particular letters, x, y, and d. D is the hypotenuse, so that's the one that has to go on the right-hand side. You learned this with the ABC, but x, y, d, same thing. All right. Now, I want to study the change of distance in time between the two planes. I do not want that distance to hit zero ever, obviously. So I just want to know how fast this distance is reducing as the both of these planes are getting closer to the airport. So I am going to clearly take the derivative in respect to time, because that is what is going to give me eventually d dt, which is the change of distance between the two planes in time. Now we're going to get a lot more stuff. So let's see, what is this derivative? Well, we have a 2x dx dt, because we took the derivative of x in respect to t, so we have to follow with the chain, plus 2y dy dt, same rules, t and y not the same variable, I have to follow with the chain, equals to 2d dd dt, which is what we are very interested in, which is the change in distance between the two planes in time. Change in distance between the planes. And now we can cancel the 2 everywhere, divide both sides by 2, and we finally have this equation x dx dt plus y dy dt equals d dt dt. This over here is our related rates model. All right, engineers and physicists and chemists and everyone else, what are these values? What is x? What is dx dt? What is y? Tell me what these things. They have
Variable.
to mean. They are variables, yeah, but what do they mean in our problem?
Your side lengths. I mean,
I don't know the units, but in physics, usually it's meters per second for distance. So I would say for each.
You mean velocity, meters per second?
Yes, that's velocity.
So what is x then?
Oh, the horizontal component moving to the left direction.
No, that will be velocity. What is x? Just x. This first variable here. What is the x?
The position of the plane.
Yes. This is distance of plane 1 to the airport. Call this plane 1. That would make the y distance of the plane 2 to the airport. Good. What is dx dt?
The distance between two planes.
Careful. You have distance divided by time. Miles per hour. What is dx dt? Guys, what measures the miles
is
per
that
hour?
velocity?
Yes, the speed of plane 1. Speed of plane 1. So, dx dt going in. What's dy dt?
Speed of plane 2.
Good. Speed of plane 2. Here's your dy dt. Now we get into what's d?
I think somebody mentioned it, the distance between the planes.
Very good. D is distance between two planes. We don't want that one to be 0, right? And then finally we have the dd dt, which is what we all want to know, which is the how fast the length is decreasing. So this dd dt is the rate at which the distance between two planes is decreasing. So dd dt is a rate at which the distance between the two planes is decreasing. Welcome to real analysis of the situation. This is what engineers have to figure out, and you will hopefully find this very interesting as we move along. So now I have a formula, I have a situation, now I understand what each one of these variables means. I have 6 variables in this problem, and I have to keep track of all of them. Because plane number 1, the one that flies along x-axis, plane number 1 wants to land. They can't fly forever. There's no fuel forever on the plane. So plane 1 wants to safely land. Plane 1 is x miles away from the airport, and plane 1 is going at dx dt speed towards the airport. Then the next plane, which is the plane 2, the one going along the y-axis, is the one that it's approaching the airport from the other side, and that one also wants to land as soon as possible. So they might be also low on fuel. I mean, you compute the fuel as they're exactly, they know how much fuel. So it's not emergency landing every time because you have fuel for another 3 minutes, right? But the thing is that they want to land as well, right? And then you have the distance d between the two planes, which is the physical distance in miles as they are approaching the airport. And then you have the dd dt, which is the rate at which that distance is closing, the rate at which that distance is going down to 0, and you do not want distance d to be 0 because that's the collision. So we started with a simple Pythagorean theorem, and as soon as we used implicit differentiation to take derivatives in respect to time, we got those speeds. Speed of the plane 1, speed of the plane 2, and the speed at which the distance between the two planes is decreasing. So all I need to do now is to pick up the numbers from the text and plug those numbers where they belong to see how quickly the distance between the two planes is decreasing. So when I want to look at these numbers and look at these problems, rule number 1, distances are never negative, but velocities are. The velocity is going to be either positive or negative depending on which way you look at the problem. So your velocity is positive if your distance is increasing. Your velocity is counted as negative, your speed is counted as negative if the distance that you covering is decreasing. Now, these planes are traveling towards the airport. That means they are closing the distance. The distance is decreasing, therefore I'm going to label both of these velocities as negative velocities. We don't deal with the vector calculus, that's your Calc 3, but maybe you already learned in physics that the speed is the part of velocity. Velocity is a broader concept because it has the speed, which is how fast you're going, and it also has the direction, meaning which way you're going. Now, when you are dealing with a two-dimensional motion where you can go left and right only, right? In that case, your distance is either increasing for positive velocity or decreasing for negative velocity. So this is something that we have to use because, you know, I had students before, they say, oh, it's moving to the left, so it's negative, or it's moving to the right, it's positive. But no, look, the y is moving up, and it's still going to be negative. And the reason why it's negative velocity is because the distance is decreasing between the airplane and the airport. So that's why both of these velocities are going to be negative. So now what they say we are having these two planes traveling at the speeds. Now, guys, you have radar, and the control tower can tell how far the airplane is. So the airplane will know that airplane 1 is 180 miles away. So that's our airplane 1. Now the pilot, well, the control can also compute the speed of the plane because they are always measuring the distance using the radar, and then you can just divide that by time and you have the speed of the plane. But the pilot can also say that the speed of the plane is going to be negative 120 miles per hour because, again, you're closing in the speed. Now, plane number 2 is going to be 225 miles away, going at the speed of negative 150 miles per hour. I know mph, but it's way better if you're using fractions because you can see that unit of length and the unit of length, a fraction and a fraction. So that should be the first indicator not to mix them up of what goes where. I would understand all the time if you mix these two up because you were not careful which one is plane 1, which one is plane 2. I understand that. What I will never understand is when two students confuse these two, because you cannot confuse, possibly cannot confuse the length with the speed, because length is completely different concept of how fast you're going. And when you're driving somewhere, it's miles per hour. Now, the problem is that they put this like this, which is completely idiotic. This should never been introduced anywhere. If you write it, because, you know, kilometers per hour, if you're in Europe or anywhere else in the world, right, it's kilometers per hour. Just go to Canada, it's kilometers per hour. Written as a fraction. So you can see the fraction, you know it's a rate. Anyway, so now what we are doing here is we still need d and we need dd dt, but you know what? This one is okay because that's what I'm looking for. So it's okay for it to be unknown. I need this one. That's the one that I really need because I have 6 variables. I need to plug in 5 to compute the one that I need, which is a 6th variable. So it's okay not to have dd dt because that's the objective of the problem. But I need this part here. And luckily, we have x squared plus y squared equal d squared, where these numbers are known, and I can compute d. Now, that is going to be now an extra piece that in these more interesting problems, you will have to determine from geometry and and so on of where can you find the extra piece. So d is equal to the square root of 180 squared plus 225 squared. And you can plug this into your abacus and figure things out. So square root of 180 squared plus 225 squared. And that gives you, oh, I'm going to write something silly just to make a point. That's going to give you 288.1405907. At which point I'm going to say, really? We're talking miles, and you're going to give me the, the decimal which this long that it's actually, fractions of an inch? No one cares. Keep one decimal, maybe, right? If you want to be really annoying, keep two for the distances in miles. But keeping all of this stuff? No, right? So, I don't know, 288.1, right? So now, I have that, and I am ready. X dx dt plus y dy dt equals d dd dt. 180 times negative 120 plus 225 times negative 150 equals 288.1 dd dt. And there it is. dd dt is equal to what? Well, approximately negative 192 miles per hour, mph, miles per hour. Look, this is important. Distance is decreasing. We see that from the formula. We know that these two planes are getting closer and closer and closer together because this is a negative number. Remember what we said. When you are closing the distance, when the distance is getting smaller, the velocity, right, is negative. Speed is always, the speed is 192 miles per hour. The negative in front is telling us that the distance is closing in. So this means, right, that in the next hour, these two planes will be 192 miles closer. Remember what the original distance was, minus 192. In an hour, the distance between these two will be roughly 90 miles, right? So this is why these things are computed. We want to see how fast the distance between the two planes is decreasing. Do they compute this by hand at the mission control? Mission control is, I know, for NASA, but the control towers at the airport, I like to call it mission control. Do they compute this stuff by hand for the two planes?
No.
No.
The answer is hell no.
Is it joulemeters? Is that the mechanism that calculates this or measures it?
Yeah, whatever it is, who makes it? What's the most important part of the whole thing? Right? It's the software, right? Computer science. And you have to program the machine to do this. Let's see why. Let's go. Oh, this is Desmos. Oh wait, I have to switch the share for Zoom people can see it. Here. You guys see Desmos?
Yep.
Yes, we can.
All right, so we're not going to use Desmos. We're going to, let me just get the keyboard attached again over here. Come on, there we go. Over here, we're going to type in Flight Radar 24. I love this website. What do you see?
Air traffic over the United States.
Air traffic over the United States. Is this 2 planes that they have to figure out where they're going, or this is thousands of planes? Currently, they're tracking about 13,000 flights worldwide. Trying to see if I can zoom in, but the tablet started overheating, so I'll have to change the cooling. So we'll take a break after this problem, I guess. I'm trying to get the New York, and here's the Washington, here's the New York. I'm trying to get, we have JFK and Newark and LaGuardia, 3 airports in the area. Then there is International Airport in Philadelphia as well. Look at the number of planes. They're also tracing some helicopters and stuff like that. That's not gonna be done by hand. You have a Joe drop a decimal and or a minus sign, and then 6 planes collide because, right? That's not gonna be like that. You're a computer science major. This is what you are coding, okay? You are coding systems that are going to track these planes. And if you have 5 planes approaching your airport, you have to know everything about those planes, their speed, their altitude, their distance. That's going to be a Calc 3 problem. If you go to the Europe, now this is live. So even if you travel somewhere, you can quickly find your plane by the flight number, and then you can find okay, there's Africa, there's England. No, that was not Africa, that was Spain and Portugal. Africa is right there on the bottom. There you go. So now there are the flights in Europe, right? That's a lot of planes everywhere, right? A lot of planes everywhere. And looking at this, you have to make sense out of all of these flights. They all have to have their altitude, and then when their time is to land, and what number of the runway and approach and so on, because, right? And when you take a look at this, right, you would say, how is it possible that you don't have like planes colliding every 2 minutes? At this point, you definitely can't fit the cars this well, right? Which is why pilots that fly these things, especially the ones that are going over Atlantic and so on, most of them have salaries over 200K a year. But you have to have a lot of flight experience for something like this, and the industry constantly needs pilots. So there's your possible career choice. But first you're going to fly the small planes and cargo planes and the FedEx planes and so on. You're going to fly that first for years, and I think it's 1,500 hours of fly experience, so you can be considered to fly the planes with 300 people plus. So yeah, that's something to consider. All right, so now all of a sudden, if you thought that this is complicated with one equation with 6 variables tracing 2 planes, yeah, go try to recompute this for 5 planes coming up, right? And you see how quickly the human how quickly the human brain gives up, right? And trying to follow all of these. It exponentially gets worse, which is why we need computer science, we need programmers, and then they need to take linear algebra to understand these complex matrix systems, because that's a lot of calculations. And it needs to be scalable and all of that stuff. So obviously, if you're a computer science major, you don't take linear algebra, you're useless on the market again, because you cannot possibly operate in the environment with, 1,000 planes, let's say, coming in without linear algebra that it's designed to fix those issues and problems. So we're going to take a break. I have to swap out the cooling pad and so on. So related rates part 2 will be coming up in a few minutes. Please, if you have any questions, go over the, these problems that we already went over. When I come back, we'll do at least 4 or 5 problems, and then we'll switch to chapter 4. So let's take a break.